Hello friends, so today we are going to solve few questions, rather 4 questions, and these 4 questions will be related to your electric potential and electrostatic energy. One second, sorry. So the first question, it is given that one of the two non-conducting spherical shells of radius A carries charge Q uniformly distributed over its surface, and other carries a charge minus Q also uniformly distributed. The spheres are brought together until they touch. What does electric field look like both outside and inside the shells? How much work is needed to move them far apart? So we are given that we have two spherical shells and each is having a radius of A, and they are brought contact with each other having a charge of minus Q or plus Q and minus Q. So let us draw the approximate figure for that, and so let us suppose this is our first, okay, and its center is suppose at the origin. So this is our x-axis and this is our y-axis, and we have second one which is in contact with this, and its center lies on our x-axis. Okay. So this is our center C1 and this is center C2, and both are having radius A. So the distance between C1 and C2 will be our 2A. C2 will be our coordinate as 2A, 0, and this coordinate will be our A, 0. And let us call this as our left side as shell number 1 and right side as shell number 2. Okay. And we have to keep in mind that they are non-conducting shells, spherical shells. And if they are non-conducting, obviously when they are brought together, the charge distribution is going to stay as a uniform. It is not, nothing is going to change. Okay. So for shell 1, we can write that is its center and is equal to 0, lies at 0, and its radius is given as A. And for shell, and its charge is our plus Q. Charge is our plus Q. Now for shell S2, second, okay, we can write that it's R2 will be at 2a along x unit vector, and its radius is same. Radius is our a, and charge is our minus q. Okay, so these are the things which are given to us. So let us consider a point inside our shell number 1. Okay. So let me redraw it again here. Shell number 1, shell number 2. This is a center, and the distance between the center is our 2a. So we consider a Gaussian surface which is inside this shell, okay, and its radius is given as r. So this is our shell number 1, and this is our shell number 2. Therefore, we can write that the field point inside the shell 1, field point inside the shell 1, and for that we have considered that r is our less than a, modulus of r. Okay. And so we know that this point is inside our shell number 1. Therefore, from Gauss law we can say the electric field due to shell number 1 at distance r will be equal to 0. Therefore, we can say from Gauss law we can write that electric field at a distance r for shell number 1 will be equal to 0 when our point is inside the shell. Now we are going to find out what will be the distance of this Gaussian surface from shell number 2, from the shell number 2. You can say distance from shell 2 center. This was our C1 and this was our C2. Okay. So let me redraw it again. So we have our C1 and C2. Total distance between the two is our 2a, and the Gaussian surface is having a radius of our distance of our r. Therefore, the distance between the center of shell 2, that is C2, and the Gaussian surface will be equal to 2a minus r. So you can say the distance from the shell number 2 center, and let us call this as our r2. Then we can say that our r2 will be equal to our r vector minus this comes as our okay. With respect to modulus, we can rewrite it like this, because one second. So let us call this as surface as Gaussian surface as S. Therefore, we can write that our r2 will be equal to r vector minus r2. Okay. And r2 is nothing but this entire. This is our r2. Therefore, we can say this as our r minus 2a, or in terms of our we can say R2 will be equal to modulus of R minus 2a. So we got the distance. Okay. And now we can easily find out what will be the field due to shell 2. Okay. And so you can say the field due to shell 2, okay, that will be outside our spherical shell. That is outside. And we know the formula: electric field is equal to 1 upon 4 pi epsilon naught q, and this is our r square and r unit vector. And for shell 2, this q charge is our minus q. Therefore, we can write this as electric field because of shell 2 at r will be equal to 1 upon 4 pi epsilon naught minus q, and this comes as r2 square and r2 unit vector. And this r2 unit vector will be equal to our r minus 2a, and in this 2a we can just write our x unit vector also. Okay, much more easier. So this comes as x unit vector divided by r minus 2a x unit vector and its magnitude. Therefore, total electric field inside the shell 1. Total field inside the shell 1, and let us call this our E, which will be equal to E1 plus E2, and we can simply substitute the values. E1 we know is our 0, so this comes as minus of q upon 4 pi epsilon naught, and we substitute our unit vector, so this comes as our r unit vector minus 2 x unit vector, r vector minus 2a x unit vector, and their whole cube. So this is our electric field inside and outside, and same thing will be true for our this shell number 2 also, because here we used shell number 1 and found out everything with respect to shell number 1, but we can use the same thing. We use everything for shell number 2, so because of shell number 2, its own electric field will be equal to 0, and only electric field will be because of shell number 1. Okay. That's why the modulus is going to help us. Okay, that's the distance is only going to, you can say everything will be same, only the sign is going to change. That's why modulus is going to help us. Okay. And in part B, how much work is needed to move them apart. Okay. So part B, we are going to find out the field due to each shell outside. Okay, then we can easily find out the work done. So we can say that field due to each shell and we can write that the field due to which is having a positive charge will be equal to 1 upon 4 pi epsilon naught q upon r square positive and positive unit vector. Similarly, we can write, because of our negative charge, 1 upon 4 pi epsilon naught minus q r square, and for this is negative and this is negative and unit vector. Okay. So the total electric field that is E will be equal to, we can just algebraically add them, 1 upon 4 pi epsilon naught, and this comes as our q upon r positive square and positive unit vector minus q upon r negative and its unit vector. And we can make use of our far field approximation, and so we can say far field approximation, which means that the distance where we are going to find out the field is much larger than their radius. Okay. Therefore, under this condition, the system is going to behave like an electric dipole. System behaves like a dipole, and we can find out the dipole moment. Therefore, we can say that the dipole moment, that is a P, will be equal to Q and the distance between the two and the unit vector. And we can easily find out the field of a dipole. Therefore, we can say field of the dipole, let us call this as E dipole. This will be equal to our 1 upon 4 pi epsilon naught 1 upon r cube, and this comes as our, let me write it, so this will be coming as 1 upon 4 pi epsilon naught 1 upon r cube, and 3 times our dipole and the distance, and this is our unit vector, and unit vector minus dipole. So this is our electric field if we consider our far field effect. Okay. Now we come to our part C. And part C, we have to find out the work done by taking these spheres in contact up to infinity. Okay. And we know, and this is based on our electrostatic potential energy. Therefore, we can say that our interaction energy of the two charges when they are in contact, interaction energy of two charges let us suppose that is given as u. Therefore we can write the general formula, that is u will be equal to 1 upon 4 pi epsilon naught charge on first, charge on second, and the distance between the two. And we know that the charge on the first is our plus q, charge on the second is our minus q, and the distance between the two is our 2a. Therefore, specifically when they are in contact, so let us rename this energy as u touch, will be equal to 1 upon 4 pi epsilon naught plus q minus q times 2a, and this gives us minus 1 upon 4 pi epsilon naught q square upon 2a. And at infinity we know that its energy is 0. So we can say potential energy or electrostatic potential energy, at infinity, if it is about u infinity, which will be equal to 0. Therefore, work done by the external agent will be the difference between the two potential energies. So we can say the work done by external agent to move the shells apart, let us suppose that is our W, will be equal to energy at infinity minus energy when they were in contact with each other. Therefore we get that the work done will be equal to 1 upon 4 pi epsilon naught q square upon 2a. And here we have to keep in mind that they are non-conducting, so there will be no redistribution of charge is going to take place. Otherwise, if they are conducting, then we have to make sure that their potential is same when they are in contact with each other. So there will be a little bit of extra work in sorting it out. Next question. It is given a thin disk radius 3 cm has a circular hole of radius 1 cm in the middle. There is uniform surface charge density of minus 10 raised to the power minus 5 cm per square on the disk. What is the potential at the center of the hole? Assume zero potential at the infinite distance. Part B. An electron starting from rest at the center of the hole moves out along the axis, experiencing no forces except repulsion by the charges on the disk. What is the velocity it ultimately attains? Electron mass is given to us. So in this case, we are given that we are having a disk, and from that disk we have removed a small portion. So this is our disk, and let us put this as center, and this portion is our removed one. Okay. So let us assume that the removed portion is having a radius of a, and the outer one, total one, is our having a radius of our r. Okay. Therefore we can say that outer radius, okay, and outer radius, which is our r, is 0.03 meters, okay, and inner radius, which is basically our hole, is having a radius of a, and that will be 0.01 meters. Okay. Surface charge density is given to us as negative. Okay. So we are given that surface charge density that is your sigma, and it is given as minus 10 raised to the power minus 5, and potential at infinity is said to be 0. Okay. So we can say our V infinity is said to be given as 0. Okay. And first of all, we have to find out potential at the center. Okay. So we have to find out potential at center C. Okay, that is our requirement in part A. So part A, and for that we are going to find out what will be the potential at the center of a uniformly charged disk of radius r, and then we come to our removed part. We can say that potential on the axis at the center of the disk. Radius we already know, so let us call this as V disk. At the center, this will be charge density and 2 epsilon naught times r. Okay. And when we removed a portion of radius a from the entire disk, so the disk which is left, or portion of the disk which is left, it is called as a annular disk. Okay. So we are interested in only annular disk, so we can write that our annular disk will be equal to our big disk minus small disk. Therefore, we can write that our at the center big disk is our, everything will be same except the radius portion. So this comes as our r minus a. And in general also, if you don't want to do it like this, because we know that whenever this is having a charge density of sigma, and we can check this the removed portion as a charge density which is having a minus sigma. Okay, in general we do it like this also. Okay, opposite charge density, but the answer will be giving us a same. Now we simply substitute the values. So this gives us minus 10 raised to the power 5, and this is 2 times 8.85 into 10 raised to the power minus 12. Radius is 0.03 minus 0.01, and we get that the potential at the center is approximately equal to minus 1.13 into 10 raised to the power 4 volts. And obviously sign is negative because disk is having a negative charge density. Okay. And part B, we have to find out the velocity of the electron. Okay. And part B, and for that let us draw the figure something like this. So this is our outer disk, and this is our inner portion which we have removed, and this is the axis, and the electron is released from the center. Obviously electron is negative charge, and this is also a negative charge, so it says that this electron moves along this axis, and we have to find out as it goes on moving. So we know that its electrostatic potential energy will be converted into the kinetic energy. So simply we can use our energy conservation. Therefore we can write that as electron moves, its electric potential energy converts into kinetic energy. Therefore, you can say energy conservation we can write it as half mv square will be equal to E times and potential at the center. Okay, and we already know our this potential at center, we are required to find out the velocity. So we simply substitute the values. This comes as half, mass is 9.1 raised to power minus 31 v square, and this will be equal to 1.6 into 10 to the power minus 19 and 1.13 into 10 to the power 4. So from here we get that the velocity approximately will be equal to 6.3 into 10 to the power 7 meter per second. Okay. So next question. It states that a dipole is centered at the origin and has charges plus q and minus q located at z plus L by 2 and z minus L by 2 respectively. Find the electric field at position R along the z-axis and also at a position R along the x-axis or anywhere at a radius of R in the xy plane. So we are given a dipole and that is given to on a z-axis. Okay, so we again dipole. Suppose this is our minus q and this is our plus q, and plus q is located at plus L by 2 and minus q is at minus L by 2, and let us suppose this is our origin. Okay, and this is our x-axis and this is our z-axis. So obviously the distance between them will be equal to over L, and so we know that we have two charges minus q and plus q, so we can find out the this electric field by the superposition principle directly. So and for that let us draw, suppose this is our origin and this is a charge q somewhere here, and we are going to find out the electric field at this point, that is our x, and the distance between the origin and this point x is, let us suppose, our r, and the distance between the charge and the origin is, let us suppose, our r prime. So this distance will be equal to our r minus r prime. Therefore we can write that electric field at distance r field at the distance, or we can say field at a position R due to point charge at r prime, and this O is nothing but our origin. Okay, for the sake of simplicity. And we can write the formula directly. So electric field at a position r will be equal to 1 upon 4 pi epsilon naught. This comes as our q, and we have our r minus r prime divided by r minus r prime and whole cube. Okay, so this is our basic formula for our electric field. Okay, or sometimes we can also call it as a Coulomb's law for point charges. Okay. And we can extend this formula for total field of the multiple charges. Therefore, we can write total field for multiple charges, and that is our E total, which will be equal to summation of all the electric field because of our I number of charges. Okay. And so we know that our electric field is, we can easily compute. Sometimes it is also called because of the superposition. Okay. It is also called as a superposition. Okay. And for that we have used the general formula for our field, and for that we have assumed that, let us assume a charge q at a distance r prime from the origin, and we are going to find out the electric field at this point x, which is at a distance r from our origin. So therefore the distance between this charge and the point is our r minus r prime. So this gives us electric field at a distance r. Please remember, this r is with respect to our origin. Okay, and this formula we get it. And this was for our single charge, and for multiple charge we can easily write that the total electric field is also sometimes called as a algebraic sum or superposition, and this will be a summation of our electric field for all the charges. Here we have taken I number of charges. In this particular question we are having I value is our 2 because there are 2 number charges. Okay. So this formula is important in case we want to find out the electric field due to our these charges. Okay. Now let us come to our original question, and the original question states that the field on the z-axis, okay, the point lies on the same axis. So let me redraw the figure. So this is our minus q, and this is plus q, and this is our origin, and the point is suppose somewhere here. It lies somewhere here. Okay, so this is our x, and this is our origin. Okay. And we know that the distance between these two charges is our L, and we call, because this point lies on x-axis, okay, so let us assume that from origin the distance of this position where we are going to find out the electric field is our z, and this is our minus L by 2, this is our plus L by 2. Okay. Therefore the distance between our plus q charge and the point where we are going to find out electric field will be our z minus L by 2, and the distance between our minus q and our x will be equal to z plus L by 2. So we reformulated our question or we can say our figure as per our own requirement. Therefore, we were having plus q charge, okay, and its position is suppose given as our r positive, and r positive is nothing but our plus L by 2 at z unit vector. And we are having minus q. Minus q is at a distance of suppose r negative, and that is our minus L by 2 and z unit vector. So now we are going to use, let us show this as equation number 1, and we simply substitute what is our r and our r prime, and we get the solution. So we can say field due to each charge, field from each charge, we can say from equation 1. And first of all, we are going to take this positive charge. So we can say our E positive will be equal to, this is q upon 4 pi epsilon naught, and the first was our r, in this case it is our z minus, and then is our r prime, that is our L by 2, and we get this our z unit vector, and similarly it is z plus minus L by 2 and its whole cube. So we can write this as our q upon 4 pi epsilon naught, and this comes as a z unit vector z minus L by 2 and whole square. So this is electric field due to our positive. Similarly, we can write that electric field due to negative charge. Everything will be same, only our r and r prime are going to change. Okay. So this comes as our z plus L by 2 z unit vector and z plus L by 2 whole cube. Okay. So, and the charge was negative, so this will be coming as minus. This is minus 4 pi epsilon naught, and we have this as z unit vector z plus L by 2 and whole square. So total electric field will be their summation. So you can say our total field, whichever E at a position of z, will be because of our positive as well as our negative charge. So we can just take out the common, that is our q upon 4 pi epsilon naught, and this comes as 1 upon z minus L by 2 whole square minus 1 upon z plus L by 2 and whole square. And we are mainly interested in solving this term, so we can just take it outside and solve it separately. So we get this as 1 z minus L by 2 whole square minus 1 upon z plus L by 2 whole square. And we take the LCM, this comes as z square minus L by 2 whole square, and this comes as a whole square, and numerator will be z plus L by 2 whole square minus z minus L by 2 whole square. So this is only calculative part, nothing much is there. And so this will be coming as our 2zl, and we get this as our z square minus l square by 4 and whole square. Therefore, we get that the electric field at the position z will be equal to q upon 4 pi epsilon naught 2zl z square minus l square upon 4, and this comes as a whole square z unit vector. And for our far field effect, we can say that our z is much larger than the distance between the two charges. Okay. So we can just simply write it by using our binomial or Taylor expansion. Okay. So this will be coming as our 2ql divided by 4 pi epsilon naught z cube and our z unit vector. And okay, next we can, or in terms of dipole, we can also write it out. Let me put it through. We know that our P is equal to nothing but our QLZ. Okay, so we can write this as our electric field will be approximately equal to this, approximately this will be 2p and 4 pi epsilon naught, and this is our z cube, where p is our ql and our z unit vector. Now we are going to find out in the equatorial plane. You can say that, you can just draw the figure. So this is our minus q plus q, and this is the point P, which is our interest. And let us suppose this is our distance r from the center. So we know this is our minus L by 2 and this is our plus L by 2. Therefore, it will be equidistant from both the ends. Okay, so we are going to get this as our r square plus L by 2 whole square and square root, and the other side will be also our r square plus L by 2 whole square and L by 2. And so in this particular case, let me redraw this specifically with respect to the direction. So this is point P and this is our minus Q. So electric field, because of the negative charge, will be, this will be our E negative, and we can divide this E negative into two components. Okay. So we get this as our, this will be E negative y component and this will be E negative x component. And because of our this second charge, which is a positive charge somewhere here, and because of this, the electric field will be away in this direction. So this will be electric field due to positive. So once again, it will be divided into two components. So this will be electric field because positive in y direction, and this will be electric field because positive in x direction. So from here we can easily see that our E positive and E negative, they are going to balance out each other. Okay. Because everything is same, and therefore we can say that E electric field due to positive in y direction will be equal to electric field at with a, or we can say their summation, much more easier to identify, will be equal to 0. Okay. Therefore the net electric field will be only along our negative x-axis. Okay. So let me write the electric field formula. So we can say electric field due to positive will be equal to over Q upon 4 pi epsilon naught, and this comes as our R minus, 1 second, yeah. So in this case we have to, cause this is the origin and the distance is our R. So let me define first the distances. Therefore we can say that field at point which is at a distance of R, and this R is our R and in x direction. Okay. And charges are same, they are not going to change, but the distance we can just write in a different way. So distance to plus Q, this will be equal to our R minus for our positive, which will be equal to our R square plus L by 2 whole square and its square root. Similarly, distance to our minus Q will be equal to our R minus R negative will be equal to R square plus L by 2 whole square and its square root. So once again we come to back to our equation number 1. You can see from equation 1 we can write that electric field to the positive will be equal to Q upon 4 pi epsilon naught, and this comes as our R minus L by 2 and Z unit vector divided by R minus L by 2 and Z unit vector, and this comes as whole cube. And we can further simplify it. Positive will be equal to Q upon 4 pi epsilon naught, and we can write this as our R is in our x direction minus L by 2 Z unit vector, and we get this as our R square plus L by 2 whole square. This comes as our 3 by 2. Similarly, we can write for our negative also. Negative is equal to Q upon 4 pi epsilon naught, only the sign will be different. R x unit vector plus L by 2 Z unit vector, and distance will be same, R square plus L by 2 whole square. This comes as our 3 by 2. And the electric field will be our summation of our both. Then we can just divide it into the respective components. So we can say electric field will be equal to because of positive and because of our negative, and negative is sign minus. Therefore we can write that E positive, E negative will be giving us Q upon 4 pi epsilon naught, and we have this as R minus R x unit minus L by 2 Z unit vector R square L by 2 whole square, and this is our 3 by 2 minus Q upon 4 pi epsilon naught R x unit plus L by 2 Z unit vector, and denominator is our same 3 by 2. Now, like I said, the x component will be equal to 0. Only z component will be remaining. Okay. So here I wrote this y, okay, but it is actually the x component, and this is our z component. Okay, let me correct it. So this is our x component, and these are our z component. Okay, because this x is given to us as z, and this x is given to us as x. So their summation will be x, and this will be also x. So we can say that our only z component will be left. We can say our z component will be equal to our minus, and we can write this in terms of our QL divided by 2, and this is our r square plus L by 2 whole square, and 3 by 2 minus QL twice r square plus L by 2 whole square, and this is 3 by 2. Therefore, we can say that our electric field on our equatorial line will be equal to minus QL divided by 4 pi epsilon naught r square plus L by 2 whole square 3 by 2 and z unit vector. Once again, we can take it as our far field effect, and far field means value of distance is much larger than the spacing between the two charges. Okay. Therefore, in that case, it is quite easy. We can just use our binomial, or we can say sometimes we can use also Taylor expansion, whichever you feel comfortable, and this comes as minus QL upon 4 pi epsilon naught and r cube and z unit vector. In terms of our dipole, we can write this as P upon 4 pi epsilon naught, and this comes as our r cube and z unit vector. So these were our electric field due to our dipole on the axis as well as the equatorial line. Okay. And next question. It states that consider a square quadrupole consisting of two adjacent dipoles oppositely oriented and placed side by side to form a square as shown in the figure. If the side length is L, find the electric field at a large distance r along the diagonal containing the two positive charges. Basic figure is given to us. So this is our minus q, and here it is also, this is also minus q, other is our plus q. And we have to find out the electric field along the diagonal at a far distance, which is our at a r. Okay. And so let us assume that this is our center. So, and the distance is, length is our L. So we are going to have, this will be L by 2, L by 2. This will be minus L by 2, L by 2, and the other will be our minus L by 2, comma, minus L by 2. And this will be giving us L by 2 and minus L by 2. Okay, so these will be our respective coordinates of our this the charges. Okay. So we get that our plus q will be our at L by 2 and L by 2, and other plus q will be at our minus L by 2 and one second. So other will be our minus L by 2 and minus L by 2. Similarly, minus Q will be at our minus L by 2 and L by 2, and the other one will be at L by 2 and minus L by 2. Okay. 1 second. Consider a square quadrupole consisting of two adjacent dipoles oppositely oriented placed side by side to form a square. Okay, yeah, this is correct. Okay. And so we get this figure. 1 second. So this is if we have a plus Q, here I put as plus Q, and this will be our minus Q minus Q. Oh, that's not possible. Okay, they are oriented in opposite direction, so we are having plus L by 2 and L by 2, and other one will be, yeah, I think consisting of two adjacent dipoles oppositely oriented to form a square. Okay, so in this case, let us okay, so we need to find out the electric field along the diagonal of the two positive charges. Okay. So for that, we can say that taking the observation point along the diagonal, and which is our at r unit vector, and we can say that it's r comma 0. And so okay, one second, let me figure it out again. I think there is some problem in the diagram. So this is our positive charge. This is at L by 2 and L by 2, and I consider that there is another positive charge somewhere here. Okay, and this is the coordinate. So this will be our if I assume that my positive charge is here, and so in that case this will be minus L by 2 and L by 2, and the negative charge is here, that is our minus L by 2 and minus L by 2. This is also my negative charge. Yes, the only problem will be the diagonal cannot be, yes, figure is correct. Okay. And we are given that this R is much larger than the L. Okay. And like we said in previous question, we dealt with the formula that the electric field from a point charge, we already know this formula, that is our E will be equal to 1 upon 4 pi epsilon naught, and in this case we are having 4 charges, so we can say summation from I to 4, and this is our Q of I and the distance between them, and denominator will be their magnitude whole cube. And in this case, for the sake of simplicity, let us say that our R of capital I is nothing but our R minus R of I. Okay, so we are interested in finding out this particular distance. Okay. And so so this was our center of the sphere, of the square, and here we are having one positive charge. Okay. And we are going to find out the electric field somewhere here, and this is at R distance, and the distance between this is our R of I. Therefore, we get this as our R minus R of I. This is our basic thing. And let us put for first charge, value of I will be equal to 1. You can say for first charge, value of I is equal to 1, which is our plus Q charge, that is our plus L by 2 and plus L by 2. Okay. And therefore we can say that our R1 will be equal to so Q is our plus L by 2 and plus L by 2. Okay. Therefore, we can write that our R1 will be equal to r minus L by 2. And r minus L by 2.